Welcome to this problem solving session. So I initially recorded this video, but I discovered the video had no sound. So now I'm simply going to just go through the problem and then explain. Instead of writing as I explain, I'll just explain what I've already written down and how to go about solving this problem. So this is a problem in Mechanics of Materials textbook from Beer and Johnston 1.28. Now in this problem, we're given, okay, let me read the problem first. It says two identical linkage and hydraulic cylinder systems control the position of the fork of a forklift truck. The load supported by one system shown is 1,500 pounds. Knowing that the thickness of member BD is 5/8 inch, determine the average shearing force in the half-inch diameter pin at B. The bearing stress at B in the member BD. So we have, it says two identical linkage and hydraulic systems control. So you can see them here, right? Now it's just to give you an idea of what linkage and hydraulic systems are. They are widely used together in mechanical and mechatronic systems, typically that's to transmit, multiply, or control motion and force. You find them in heavy equipment like the forklift, robotics, automobiles, or automotive systems, and manufacturing machineries as well. Now, for a forklift, these systems, what they do, that's the linkage and hydraulic cylinder, they simply work together to lift, to tilt, steer, or stabilize loads. The hydraulic cylinders are the ones that provide the force, while the linkage control the geometry and guide the motion. So now, for this problem, we have, it says two identical ones. They control the position of the forks for this is the fork here, right? It says knowing that the thickness of member BD is 5/8 inch, determine the average shearing stress in the half-inch diameter pin at B. Now, this is the fork itself, right? Now, to also find the force here, of course, we should expect to have, this is the pin, we can expect to have two forces. So first of all, we draw the free body diagram of this, which is given here. Now for this one, pardon my diagram, it's not the very best. At this pin B, of course, we have two forces, Cartesian coordinates, right? Bx and by here. We have that. Now the force, the load supported by this system is shown. So here we assuming it's a concentrated load, or the points load, sorry, at this point, which is 1,500 pounds here, and it's acting at 200 inches. That's in terms of distance with respect to point B, actually. Respect to point B. So this is B. Respect to point B here. Now for point E, we have, you see, this part is looks like a reaction force acting at this point here, right? Pointing towards here is E, or it's technically EX, sort of, right? Yeah, that's the force acting at this point. That's 24 inches from B. Now, in solving this problem, it says determine the average shearing stress and bearing stress. Of course, in find stress, you need force, right? So, and area. So now the force acting at this point, so we have two, By, that's in the vertical, and Bx. So that's the starting point. And in order to do that, we already have the free body diagram, which is here. So if we take moments at point B, of course, since we have these are unknowns, we don't compute this at this point, right? We take a moment, we can first find the unknowns, which we already have one as E. So now the first point is to take moments about point B. Now this is B here. We have one force E, and we have this 1,500 force. Now look at this. If you are applying force here, right? This applying the force at this point here, there's tendency for this force to want to move this, right? To tilt this, that's a lot. To want to move this like this. That's in the in the clockwise direct. I mean, oh no, sorry, in the anti-clockwise direction. So because you're doing this, sorry, if you're moving this and there's a force coming here, this one's trying to move this here, 1,000 force, 1,500, but this force E is trying to take it upward, right? Now it depends on the, of course, the part that tend to dominate will depend on what the controller is trying to do, basically. But if you look by principles of moment, this bringing it downwards will force it to rotate clockwise, right? This will move anti-clockwise, right? So that's why if you look at E, you see it's E. E is the force here. With respect to to where you're taking, you're trying to find the effect of the force at this point as the moment, the turning force, the turning effect at this point. So that's 24 times E. Now, this is acting downwards, right? Trying to turn this way. So that's 1,500 multiplied by 20, because this is the vertical force with respect to the line of action of this point B here. So that is 1,500 times 20. Now the sum of forces at this point here, or I mean at any point you're taking moment, is 0. That's equilibrium of forces. So with that, if you of course this one, if you take this one to the other side, this negative becomes equal to this divided by 24, which is this here. We get 1,250 pounds. Now, similarly, we have Cartesian forces. We have Bx, we have E, all pointing in the x direction, and we have 1,500 and By, all in the y direction. I mean, they're in the y direction. So, sum of forces in the x direction, sum of the forces in the x direction, and we have E is pointing this way. That's positive. B of x, or Bx, sorry, is positive as well. So E plus Bx equals to 0. Bx is equal to negative E. So we already have E. So so B of x is in the opposite direction, or Bx in the opposite direction. Similarly, for the y-axis, we have By here and this, right? Of course, so By is facing upwards, since that's our convention. Upward is positive and negative is downwards. I mean, negative is downwards. So By is equal to 1,500 pounds. So that's how to find. I mean, now we've gotten not only the moments but the sum of forces. We've got the moment. I mean, we've taken the moment about point B, which has enabled us to get the force E, and now we're going to find the components Bx and By. Now, to find the stress in this point, either if it's the bearing or the shearing stress, the force you're assuming the force acting in unison, the resultant force, irrespective of the direction, is what we are going to be using. So that's why here we are using this, right? So again, at this point, the effect of this on this point, I need the resultant force. That's the force that just kind of unifies both of them. We're saying Bx squared plus By squared equals to B squared. Of course, with the units, when you square this turns all positive, and we get 1,952.56 pounds, and that's the force at B. Now for shearing, the question says determine the average shearing stress in the half-inch diameter pin. So the pin here is half-inch diameter. Then the thickness of this, because the pin is going through the pin is going through this member BD, right? And that thickness is 5/8 inch. So we're going to be finding the average shearing stress and the bearing stress. Just in case you don't know what the shearing or bearing stress is. So for shearing stress, when the force acting parallel to the surface attempts to slide one material over the other, that's shearing stress. Just look at it as like if you have like a composite or plywood, basically different layers, right? If it's not well glued to, I mean, they tend to want to move independently. That's what shearing stress is, sort of. That's the easiest example I can give. Then for bearing stress, you look at it as a comprehensive contact stress between two mating surfaces. That's why for the bearing stress, because of course, when you're applying force, the contact, we then need to account for the thickness. So for the shearing stress at point B, so here you can either use B or use F of B in case it's confusing to you. Of course, you first find the pin. You have to find the area of the pin, which is either pi d squared or by r squared. By d squared is easier for computation since you don't need to compute anything, or one step of computation is eliminated. So that's pi multiplied by 0.52 inch squared divided 0.5 inch squared divided by 4. Then we get 0.19634. I mean, just for accuracy, inches squared, right? Because this is 1 inch. When you square that gives you inch squared. Then the shearing stress is typically the force divided by the area of the pin, right? To give us this B, which we had gotten here, divided by the area of the pin, which is from here, to give us 9,944.3 pound per inch square. Now for the bearing stress, beyond just using the force and just then the diameter of the pin, you also need the thickness, because for this case it's going through that. When you put the pin through, the effect lasts up to the thickness BD. The pin here, the thickness of this of the parts, it applies to that. This is BD, remember. So that's why we are using, because this is the formula. So that's B over DT. Now, this is already in pound, half inch, thickness 5 over 8. So if you compute that, you get 6,248.2 pound per inch squared. I hope this helps. Cheers.